Hello everyone, welcome to our virtual lab. Today is April the 9th, Thursday. It's now 1 o'clock and I would like to welcome you to our last virtual lab this semester. We do have one class meeting next Thursday, 1 o'clock. For final exam. Obviously, we will not have an opportunity to do the lab practical, but there will be about 30 multiple choice questions. There will be about 30 multiple choice question next Thursday around 1 o'clock. That will be it. We will not have an opportunity to do the lab practical schedule at the beginning of the semester, but we'll just have the multiple choice online exam, just the way you have been taking the quizzes. All right, so pay in mind that we do have one class meeting next Thursday. As you plan for that exam, continue revising past or previous quizzes. There is a study guide I did send out. Please use that study guide. Use any other resources. Yes, the exam will be timed. It will be about 1 hour for 30 multiple choice questions. You will need a calculator. You will need a periodic table. I'll send you. More material once I look at the question and determine what you need for every question. If need be, I'll make it available for you. But in the meantime, you obviously need a calculator. You will need a periodic table. I'll be available as well, just in case there'll be any question. I'll be able to respond right away. I'm still working on labs. That means the grading and putting the grades on Canvas gradebook. If you haven't seen previous work you turn into me, I haven't got a chance to create those labs or pre-labs. I've been working on putting stuff online, and we are in a position, or I'm in a position rather, to go back and create those hard copies. You turn it to me. In case you didn't see, you haven't seen previous work, please send me an email and I will respond. If you have any question, you can also send me an email and I'll get back with you within 24 hours. Yes, the review, somebody is asking about the review. I do have the study guide, but if you want to, if you have a particular, all right, a particular question or concern on a particular concept, please let me know and I'll be available for review as well. Somebody is asking about the review. I do not have the study guide or practice question for that case to go through, but I'll be available for review. For example, if I say, you need to know something about electronegativity and you don't know anything about the electronegativity, I'll be more than happy to work one-on-one with you or a group of you to go or brainstorm that concept of electronegativity. So look at the bullet point, all right? I do have some sort of study guide in bullet points that you need to know something along this line. You need to know about molarity, for example. How do you calculate molarity? That's something you should know from the lecture and from what we learned previously, all right? I will be more than happy to go through the study guide, what you need to know, focus on those bullet points, make your own notes, and you should be good to go. All right, so without wasting my time, it's now around 1:05. What I want to do is make the quiz available. You'll have about 30 minutes. We'll come back here and I'll walk you through how to complete the data sheet for drawing and understanding Lewis's structure. Please do not leave. I'll come back here, walk you through on how to complete the data sheet, and you will submit through Canvas on the respective folder, I've seen some wrong labs or some wrong pre-lab showing up in the wrong folder, and I just respond saying that this is the wrong lab, even though you may think that, oh, I sent it to him through email as an attachment. I'll not, you know, I'll just respond back saying that this is the wrong lab or this is the wrong pre-lab. Do not attach or submit your work in the wrong folder. You better email it to me and I'll give you the direction on what to do. So wait a minute, I'm just going to make the quiz available. I'm going to make the quiz available, all right? Just sit back, I'm going to make the quiz available for you. All right, everybody, may I have your attention? Let's get started with our lab session. I want you to have a piece of paper and a pen so that you write down the notes. Please have a piece of paper and a pen so that you write down the notes what I'll go through. As far as our experiment is concerned, that is drawing and understanding Lewis structure. I'd like to share my screen and show you some of the documents I do have. There are some documents I have on here. I'm going to share my screen on this end and see if you can see. Let's see. All right. Sharing the screen. You can see that I have a couple of documents drawing and understanding Lewis's structure. First of all, before even we talk about the Lewis's structure, who was Lewis? This is the name of an American chemist who proposed that when elements on the periodic table react to form compounds, make use of their valence electrons. Scientists before they knew about the valence electron, of which you know how to find the or determine the valence electron, given the periodic table, you can be able to, or you should be able to determine the number of valence electrons without necessarily, you know, drawing the electron configuration. You don't need to write the electron configuration to determine the valence electrons. Let me go back to Lewis. Why? Or why do we have to look at this? He was the first person to say that when elements react, they make use of their valence electrons. And what are valence electrons? Electrons on the outermost shell, electron on the outermost shell. For main group elements, that is the A, all right? That is the A on the periodic table. Those group numbers with the Roman numeral and the letters A, those are the main group element, and the group number corresponds to the number of valence electrons. If you look on this, table 1 in the lab manual, you don't need to write the electron configuration. You don't need to write the electron configuration shown here in order to determine the number of valence electrons. You have to look at just what? Look at the group number on the periodic table. This is in group 1 valence electron. This is in group 4A, this is gonna be 4 valence electron. This is in group 5A, it's gonna have 5. This is in group 6A, it's gonna have 6 and so forth. Except for helium, all right? Except for helium is group A, obviously it doesn't have 8 electrons. So that's how you use the periodic table to determine the valence electron. You'll see other element on the in the data sheet, which you need to use the periodic table to determine the total number of electrons. So to understand and master the Lewis structures of molecules, we need to be able to determine the valence electrons of compounds, the total number of valence electrons. And dot symbol, of course, is only the dot, and the chemical symbol representing the element, the element, and the dot represent the valence electron. So Lewis was the first person to propose that when element react, they make use of their valence electron. So we're gonna be talking about the valence electron. You're gonna be seeing valence electron in Lewis dot structure. If we had an opportunity to, to come to lab and build models, all right? Model is something like representative of the actual, and then we could see the actual shape of those molecules in 3 dimensions, all right, in 3 dimensions. And to understand the 3 dimension modeling, we need to understand the Lewis structure. So yes, somebody's asking, am I going to post the video on Canvas? If you want, I can do that as well. I can post the YouTube one. I can post to YouTube later on. So coming back to Lewis dot structure, let's see the how to determine, or how will we going to fill in, how can we fill in the data sheet? How can we fill in the data sheet? Yes, you can fill in the data sheet from sets of rules. I do have some sets of rules. In the lab manual, there are some examples, all right? There are some examples on how to draw the Lewis structure. Cyanide, for example, H2O, and I think other compound which is given. This is the cyanide, H2O. Yes, this is phosphorus trifluoride. We have there are 3 examples in the lab manual on how to draw the Lewis structure, on how to draw the Lewis structure. You can, all right, you can use this on the lab manual to try and understand. But I do have my own, synthesized rules, which I have found over the years that it is easier to come up with those rules. Let me see those handouts. Let me just show you sets of rules. Here are the rules I'm talking about. The rules I have here on how to draw the Lewis structure for a compound. I'm going to walk you through this using H2O here as an example. How do we end up with the Lewis structure for H2O right here? If you try to follow the example and I say, all right, just follow the example in the lab manual, and you will not be in a position to understand even what's going on here. Like, suppose I give you other molecule which is not in the worked example, how are you going to proceed? I'm going to use the rules, and I'm going to post on Canvas those rules in our document. And here are the rules, all right? And I'm going to use H2O and see how you'll end up with this Lewis structure. This is all what you need. The structure, the last structure you need here, all right, is what you need to complete the data sheet, each and every item on the data sheet. So I'm going to redo the H2O here using the rules I have right here, from rule number 1 all the way to rule number 6. Sometimes we may not go all the way to 6. There's another document which I'll show you on how to predict the electron domain geometry and the molecular geometry. Let's see, first of all, how do we use the rules here to determine the Lewis structure for H2O. If you look on the screen here, all right. If you look on the screen, I do have my iPad here, and I'm going to use the rules here to show you how to arrive at the Lewis structure for H2O. So for my H2O, all right, this is the water molecule, all right? You know, water molecule, H2O, all right, H2O. How do we write the Lewis structure? First of all, rule number 1 here states that find the total number of valence electrons in the molecule or polyatomic ion by saying that hydrogen is 1 times 2, we have 2, and this is 2 valence electrons. Oxygen here, we have 1 oxygen times 6, this will be 6, and we have 8 valence electron, 8 valence electrons. This is the number of electrons in water molecule. Rule number 1 is to determine the total number of valence electrons. Using the periodic table, hydrogen is in group 1, oxygen is in group 6. You got to multiply by the subscript. So we need to know how many, how many electrons do we have on the total molecule. If it is polyatomic ion, I'm going to come back to that later for part 2, and for part 3. And then number 2 is draw the Lewis structure. Right here, this is rule number 1. Rule number 2, the skeleton is understanding what is the central atom, the external atom. We should have 2 types of atoms here, external and what? And the central atom. Always the least electronegative element is the central atom. That means the one which is on the left side of your molecule when you write that. So the structure here for the skeleton here I'm talking about is this structure. Hydrogen, the 2 hydrogens are bonded to oxygen. Oxygen is the central atom in this case. Now, root number 3 here, subtract a bonding electron, BE. Bonding electrons stand for each line. You know, we have what? We have 2 electrons here. We have 2 electrons here. So that, you know, we have 4. So I'm gonna subtract 4. We remain with 4 remaining, 4 electrons remain. These are the number of electrons remaining, And in these remaining electrons, the first priority octet rule, you read about the octet rule, says that when elements combine or form chemical bonds, they share their valence electron in such a way that they end up with 8 electrons. We call it octet rule. The octet rule, except hydrogen. So in satisfying the octet rule from the remaining electrons here, you see these remaining electrons on my iPad right here, there is 4 remaining electrons. What I'll do with these 4 remaining electrons right here is to satisfy the octet rule on the external atom. That means atoms hooked up to the central should have 8 electrons. Except hydrogen right now, we don't have to worry with about hydrogen right now because it already has 2. It's like helium. So the 4 remaining goes to oxygen. The 4 remaining electrons, and they should be paired up. So I'm just gonna have the two electrons on that oxygen at the center. You see how I was able to arrive at the Lewis structure for H2O. Right here, what you see on the screen is the Lewis structure for H2O, which is at the bottom right here. You can see it's at the bottom right here. This is the Lewis structure for H2O. If you follow the 5 steps given in the lab manual, you can arrive, or you will arrive at the same conclusion. But I do like this because it applies to atom molecules. For example, polyatomic ion. I'll show you one with polyatomic ion. With this structure here, all right. With this structure here, you should be able to complete the data sheet. You should be able to complete the data sheet by using the structure. All right, by using the structure, let me just minimize this. I'm just going to show you what you need to. On the structure here, if I have the H2O, let's go back to H2O. You see the water, you need to fill in right here. You need to fill in right here. You need to fill in here, right? You need to fill in it. You need to fill in here. How are you going to fill in this table. There is a handout which I'll send you. This handout you see here will help you in, this handout will help you in completing the remaining portion of the data sheet. First of all, the number of valence electrons for H2O, we end up with 8. So if I was to write the number of valence electron, I'm just gonna put 8 here. Electron domain geometry and the molecular geometry. Electron domain geometry and molecular geometry. You will use this table to write the general configuration for your molecule using the central atom. This is the central atom. Look, let's go back to this diagram here. I'm going to show you how you use the central atom. This is what I'll put it in the box, and what you need to be using this diagram or the box or the illustration, whatever you want to call it, on the central atom to come up with this configuration here. So what I'll do is write the configuration where A stand for, all right, A stand for the number of, here A, this is the central atom, stand for central atom. B, all right, B here is the number of what? Number of external atom. And E stand for, or I should have erased this. Let me erase this. We don't need this anymore. We have used the 4 electrons. So if I want to, I am writing the electron configuration. This stands for number, all right? This stands for number of lone pairs, all right? Lone pairs of electrons. So that is the configuration you need to use. So if I look at A, all right, I'm just gonna write this using this oxygen. I have A, that is the oxygen, B2, all right, P2, and lone pairs are 2, so E2. So I have E2. This is my configuration for H2O. H2O has A2P2, and if I align this right here, the electron configuration for H2O, let me align this so that you see. This is the configuration for H2O. A, P2E2. And if I look at the molecular, you know, see from there, but the electron domain geometry is this column right here. And for H2O, this is tetrahedral. And the molecular geometry is V or pen shape. V or pen shape. So that's what you need to know in terms of the using this handout. So for molecular, if I look at the molecular for H2O, it's gonna be electron geometry. This is tetrahedral, and molecular geometry. This is a V or pen shape. All right, that is a pen shape for molecular geometry and the electron domain geometry. So I want you to use this, you know, the configuration I have here. Once you derive your Lewis structure, it's gonna give you the configuration on the central atom, in order to complete the molecular geometry and you see this molecular geometry and electron domain geometry. Gonna use this is the domain geometry and this is the molecular geometry. So you write down here the electron domain geometry and molecular geometry using the handout. Still on the handout, you can look at the bond angle for H2O. It should be 10. I see this is 104.9. For H2O, it is 104.5. 104.5. So I'm just gonna put 104.5 for H2O for H2O. That is how to complete the first 1, 2, 3, or 4. We are done with each column. I mean each box right here in each problem for part 1. Now for formal charge, all right. For formal charge, there is an equation in the lab manual. Which I think right here, there is an equation which I will just have to rewrite. Formal charge. So when you have resonance structure, you can use the formal charge. This equation given here, you can use to write the formal charge of your compound, and the formal charge, I will rewrite again the equation you can use to derive the formal charge of a compound. You can use that, but when I look at this equation, equation 2, you may not be in a position to figure it out what is going on. All right, given this structure for H2O. Remember, we are looking at the formal charge for the central atom. Central atom is oxygen. How do we calculate the formal charge? If you try to use this equation right here, you may not be in a position to really understand. But look at my iPad. Down here, I will write down the equation on how to find the formal charge. Using this equation, formal charge, F for formal charge, is given by the valence electrons of that element. For example, right now, oxygen is in group 6, minus non-bonding electron. This stands for non-bonding electrons. How many non-bonding electrons? Not electron pairs. Non-bonding electrons. These are the non-bonding electrons. 1, 2, 1, 2, 3, 4. I have 4 non-bonding electrons on the central atom. Look at the box, not outside the box. Minus, I have bonding electron, PE for bonding electron. This is the equation. You may want to substitute in place of this equation for finding the formal charge. You know, when they say assign electron, you're like, okay, what is more than what you see just here? You think that it is just one file. Assign electrons right here is summarized by this equation: non-bonding and the bonding. So if I do for oxygen, I'll write down here and say 6. All right, 6 is the valence electron for 6 is the valence electrons for oxygen, minus 4, which is non-bonding electrons. Non-bonding electron, NP here stands for non-bonding electrons, minus a half, all right? Minus a half of the bonding electron, which is what? Which is, if you look at the bonding, this stays a bond here, and then there is a bond there. Each bond has what? Each bond has 2 electrons, 2 electrons. So a half of 4, all right? This is the same as when you cancel that 2, so it's gonna be 6 minus 6, and this will give you 0. This is 0, and this is the formal charge of oxygen in this case. So if you are writing your own notes, I'll recommend that you use this equation. However, if you understand what is going on here, you can still use that to find the formal charge. That is what is going on in to arrive at this. So if you look at the electrons, they are talking about a sign. Each electrons they are talking is how you use, but if you can read and understand this as well, that's fine. It's how to find the formal charge of the central atom. Bear in mind, not all problems will have a central atom. If I look at, for example, carbon monoxide, if you look at carbon monoxide is CO. So where is the center? It has been specified here that you have to find the formal charge for carbon, That's how you find the formal charge. Using the equation I just gave you below H2O, all right, here it will help you in, determining the formal charges of the element in question. Now, as far as polarity is concerned, this column right here, or this row, or this particular portion of the data sheet, you need to read on polarity. Polarity of the bonds and the polarity of the molecule. It does not mean when you have polar bonds in a molecule, not necessarily that the molecule is polar. You got to look at the electron distribution within the molecule and say, all right, this portion of the molecule has high electron density, The polarity has to do with electronegativity, and electronegativity is basically the ability of an element to attract electron toward itself in a covalent bond. So if you look at, before you talk about pick up the bond polarity or the molecule, whether it's polar or non-polar, you need to draw look at the molecular geometry of the molecule. Let's see. How are you going to figure it out, the molecular geometry of H2? It's not like in 2 dimensions, as I say. To understand this, you got to look at the in the data sheet, or I mean on table 2. All right, you look at the structure, for example, of the molecule. For example, H2O. If you look at H2O, it represent, or it look like the structure F on the data sheet. Let's look at structure F. For F, all pen shape will have this configuration. All F will have that configuration. And if I redraw now to state whether it is polar or non-polar, you got to come back to these cartoons or illustration of the molecular geometry and redraw it again. And using the periodic table and the trend on the periodic table, remember electronegativity increased from left to right, and the decrease going down the periodic table. So if I draw the H2O, I can have this diagram H2O, where I have hydrogen here and hydrogen on this end, and the two electrons. This is electron cloud. All right, this is electron cloud, and this is electron cloud. If I look at oxygen here, it is more electronegative than hydrogen, and electrons are displaced in that direction, and the electrons are displaced in that direction, and the net displacement is in that direction. So this is partially negative part of the molecule, and this side is partially positive side of the molecule. We say that this molecule is polar. So I know this is polar molecule. I know it is polar molecule. However, if there is equal sharing, then the molecule is non-polar. So polarity has to do with the electron distribution on the molecule, and that's what I'll do as far as polarity is concerned. I know you will use this one to determine the configuration. You will also need this table right here for hybridization. My table here doesn't have anything to do with hybridization, but this one, table 2 on page 231 is handy in determining the electron hybridization, not geometry, hybridization. And from our H2 here, it has 4 domains with 2 lone pairs of electron and sp3 hybridization. This is what I'm looking for. So you have to look at your configuration that, if I look at this, there is 1 central atom, and remember the subscript here for all these configurations stand for domains. 4 domains, 3 plus 1, 4 domains, 2 plus 2, 4 domains, 5 domains. If you look at these, 2 plus 1, 3 domains, and then we have only 2 domains. We have a lot of domains. So if I look at H2O, 2 plus 2 is 4 domains, so I know it's gonna be on this domain. And electron domain geometry, tetrahedral, and since there were 2 lone pairs, non-bonding, 2 lone pairs, 1 lone pair. See, if you have other type of configuration, all of them will have sp3 configuration. So this is where you will come for filling in the data sheet on electron domain, geometry, electron domain geometry for your compound, So that is how you complete the electron domain geometry by looking at the structure. So that is hybridization. That take care of hybridization of the central atom. Any question on part 1? Any question on part 1?
No.
No question? Did somebody use a chat? Maybe, let's see. No question. All right. So that is what you will do in part 1. I want you to, go to part 2, which will call for an understanding on organic molecule. Organic molecules or organic compounds are those compounds made up of carbon, all right, and hydrogen. Organic compounds are those compounds which contain hydrogen and carbon. And from the Lewis dot structure for carbon form for bonds based on the lone pairs of what? Based on the lone pairs of our electrons around our carbon form only 4 bonds. Look at this, 4 dots. That means single bond. It can form a bond. Cannot form more than 4 bonds. So in part 2 here, part 2, all right, part 2 here is on organic compounds. And those organic compounds are compounds containing what? Containing hydrogen and carbon, and sometimes functional group with oxygen. All right, let's see how you interpret an organic molecule. Look at my iPad. If I erase this, I just want to, I think with one, I can go to next page for organic molecule. All right, let me have something like C7 H16, for example, H16, 16 like that. All right, H16 like that. This is an organic molecule, You start by building the skeleton. The skeleton is made up of carbon chain. You have to form a chain of carbons. Here I have 7. So I'm just gonna write C, 1, 2, 3, 4, 5, 6, and 7. You see, 7 chain, because I know subscript is 7. And what I'll do is, now ask myself, from your understanding of, the maximum number of bonds carbon can form 4 bonds. So the first carbon, I have 1 bond, so I need 3 more. So I'm just gonna form a bond here, and a bond there, and just put that for, just gonna change this, make it easy. Hydrogen here. This is hydrogen. 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 I didn't mean to go back there, but anyway, let's see. CH7, it was CH7, H16, and basically what I'm trying to say is 1, 2, 3, 4, 5, 6, 7. What I'm trying to say is each carbon has hydrogen hooked up to it, and if you count it, it will add up to 16 hydrogens. It will add up to 16 hydrogens. It will add up to 16 hydrogen. I do have others on that side. You don't see that, but this carbon right here look exactly the same as that. You don't see it here. I do have another hydrogen there, and that will be the structure, the Lewis structure here. All right, you can change that to dots, but that's the structure I'm looking for. I don't have any lone pairs. Just build the skeleton fast. How are you going to form or complete this column right here? Number of sigma bonds and number of pi bonds. Number of sigma bonds and pi bonds. First of all, I know you're familiar with single bonds. I know you're familiar with double bond, and you're familiar with triple bond, with a single line, 2 lines, and 3 lines, and you know how many electrons are in there. But with respect to sigma bonds and pi bonds, in pi bonds, all right, pi bond, this is what I do have in terms of pi bonds. In terms of pi bonds, one, this is a single bond. It has this is single bond. This will have only 1 sigma bond. 1 sigma bond. All right, and then when we come back to this, the double bond like that. All right, double bond. This is double what? Double bond like that, and this comprises of 1 sigma bond and 1 pi bond. 1 pi bond. This is a bond right here. So you need to know what is what constitute the double bond, single bond. And lastly here, lastly there is our what? Is our triple. I meant to say triple. I don't want that. I just want only one line there. And this is a triple what? Triple bond. Triple bond. This is made up of one sigma bond and two pi bonds. Two pi bonds. This is sigma bond, and this is sigma bonds. Right. Yes. This is what you should know before you answer this part on the data sheet. That how many single bonds do I have? Let me go back to my structure for my example here. I'll count and say how many single bonds do I have? How many single bonds do I have? How many double bonds do I have? Count all the single bonds, and then that will be equivalent to your sigma bonds. Do you see any pi bonds? No, I don't see it. So you just say 0 pi bonds. You just say 0 pi bonds, and then you move on to the next. All right. Now, in terms of alkenes, let me just go back to add another page. In naming of organic compounds, the ending tells you whether there is a double bond. If I say A and E, we call these alkanes, and they have single bonds. If it is E and E like that, this is alkenes like that, E and E like that, alkene, and this has double bonds. They must have a double bond somewhere, either 2 or 3 double bonds or 1 double bond, but there must be a double bond somewhere if you have A and then Y and E, these are alkynes, all right, and they must have triple bond, triple bond. So when you see the naming here, it's a hint to tell you that it has a double bond, it has a triple bond, it has a double bond or triple bond. I'll pick one from the data sheet and see how you go about with this. If I go down to say this propane, I know all of them will have a double, single bonds because it is A and E. All of them have single bonds. If I look at E and Y, or Y and E, that means it's got a what? Triple bond or double bond, whatever you want to see. Yeah, A, Y, and E, triple bond. So let's see the last one here. I'm just going to show you how you start with, or how do you generate a triple bond or double bond. For using this example right here, with the 3-carbon chain, all right, with the 3-carbon chain, I will show you how to build a molecule based on that. So what I'll do here is write the structure. This is where I'm trying to, this is where I'm right now. It is a 3-carbon chain molecule. So this is going to be, look at this, carbon, carbon, carbon. I started off by the skeleton of the molecule, that's this chain. And the fact that I have E and E, that means there should be a double bond somewhere. Doesn't really matter whether I put up front here or I put front here. You don't need to, if you form just like that, you'll be, contravening, or you will not have a place to put extra electrons, not electrons, but hydrogen. If you do that, we are supposed to use 6 electrons. Where are you going to put hydrogens in that case? You'll be left with some hydrogen. So the best way is just start with one double bond first. And if need be, you'll just go back and make the double bond if it is needed. So let's start off with one single bond, one double bond first, and using the understanding of how many bonds does the carbon form 4 bonds. So this last carbon here needs 2 more hydrogens. Doesn't really matter where you put. It can come here, all right? It can come down here, can go up there, and I have my hydrogen there, and I have my hydrogen there. I have used, all right, out of the 6, I've used 2. I have 4 more. So if I have 4 more, this needs 3. All right, this needs 3 hydrogen, and this is hydrogen right there. I've used 3 hydrogens, and the last one right there, hydrogen. That's how you you end up with your Lewis structure. Lewis structure. That's how you end up with the Lewis structure. If you count the number of carbons, there are 3. If you count the number of hydrogen, there are 6. And because it is ENE, that means there must be a double bond. And then when you go now to the sigma bonds, you look at here. Look at here, this column here, how many sigma bonds? Remember from this, from here, sigma bond, one single bond, that means 1 sigma bond, right here. 1 sigma bond, single bond. If I have double bond, that's how much I have. You need to use this to know how to determine the number of sigma bonds. So if I go back to, here, all right, I'll say sigma bonds, there is right here, let's see, she'll have the, right there, I have 1 sigma and 1 pi bonds. So that if I count the number of pi bonds, I'll say 1, 1, 2, 3, 4, 5, 6, 7, 8. I have 8 sigma bonds. All right, 8 sigma bonds. Don't say 1, 2, 3, 4, 5, 6, 7. There is 1 right there. And then pi bond is 1 pi bond, 1 pi bond. That's how you complete the last column on pi bond. Complete the last pi bond. That take care of part 2. That take care of part 2. You'll have to either look at in the lab manual how to draw the structure for ethanol, build the molecule, how to organize electrons around oxygen. Okay, oxygen. Any question? Any question? Eric, yes, hopefully you'll have the playback. Somebody was asking about playback. Hopefully you'll be able to do that. First of all, I'm recording right now on my computer, and then I'll upload on YouTube. You'll be able to watch on YouTube. So I'm gonna post that. Hopefully you'll be able to play back for that. I'll try to adhere to that settings. So that is part 2. Let's see, part 3. It's similar to part 1. Part 3 is similar to part 1 in the sense that we'll go back to the counting the number of total valence electron, drawing the skeleton of the molecule, and the central atom, and and how to end up with that. But this time around, we will be working with ions, and remember, ions are either positively charged or negatively charged. Positively charged or negatively charged. I'm going to use, all right, I'm going to use sulfate ion as an example. Sulfate ion is SO4 with an overall charge of -2. This is sulfate. They expect you to have mastered it, commit to your memory, the chemical structure or chemical formula for ions, all right? Using the rules we looked at before, first of all, you have to find the what? There are some rules we looked at before, that is finding the number of total valence electrons, number of total valence electrons. This is the rule number 1. Total number of valence electrons, sulfur. All right, sulfur is in group 6, oxygen is in group 6, and then we have this is times 1, that's gonna be 6. 6 times 4, this is 24. I end up with 30 valence, right? Valence electrons, like that. Valence electron. There is something you need to do with the overall charge of -2. Overall charge of -2. All right, because of the 2 here, because of these 2 right there. You see these 2, we will add +2. We'll add our +2. So we have 30 what? 32 valence electrons. That's how you find what? That's how you find the total number of valence electrons for polyatomic ion. If it was overall 3, then we add 3 electrons. If it is overall charge of -1, we add 1 electron. If it is overall charge of positive, you subtract. This overall charge of -2 means there are additional extra electrons. Remember, electrons are negatively charged. So the number of electrons we should be working with is 32 here. Rule number 2 is drawing the skeleton of the molecule. The first thing is to draw the skeleton of the molecule. I don't like this color. Let's see if I can gonna give me this. I think this is visible with the oxygen hooked up to the central atom like that, We have taken care of the skeleton of the molecule. We subtract, rule number 3, subtract the bonding electrons from the total number. So I'll do my math by saying 32 minus bonding electron. Okay. 2 electrons, right there, 2, 2 there. So minus 8 electrons. These are the bonding electrons. We have 2 on either side. And what will remain here is 24. 24 remain. 24 remain there. Okay. Out of the remaining, first priority in satisfying the octet rule is are the external atoms. What is in outside? So I'm just gonna go and erase this right here so that it's gonna be clear how you distribute the electrons. So I'm going to distribute the electrons around each oxygen, all right? All right, these are the electrons, these are the electrons, these are the electrons, these are the electrons, these are the electrons. So I've distributed 24. If I subtract 24 minus 24, 0 remain. If something remained here at the end, you just give it to the central atom. You just give it to the central atom. Don't worry about, you know, the, don't worry about things that it has max, the maximum it can accommodate or it can take. Once that is done, do the inspection. Make sure that the octet rule is satisfied by all elements in the compound. And right now, all elements satisfy the octet rules. You need to pick parentheses for polyatomic ion, you need to do this. You don't leave it that way. This is what you need for polyatomic ion, and include your overall charge. Your overall charge. That's how it to go about with polyatomic ion, and I think this is relevant. This concept is relevant for part 3, where you will encounter polyatomic ions. Polyatomic ions. All right. Any question on how to handle polyatomic ion? One thing before we end, give me 5 minutes and we'll be done. I did not show you how to navigate a compound with double bond. I talk about double bond is step number 5. All right, step number 5. How do you generate a double bond in your compound? Let's see. I'll give you an example of a compound which you'll have to make a double bond. An example is sulfur dioxide, SO2. This is sulfur. We call this sulfur what? Sulfur dioxide. Sulfur dioxide. Because we have two. We do the same thing we did before. That is finding the total number of valence electrons. Sulfur is 6. All right. Sulfur is 6 times 1. This is 6. And then oxygen, we have 2 of them. And this is 12 or 18 electrons. 18 electrons. All right. This is 18 electrons. So once we have that, we draw the skeleton of our molecule S. All right, this is bonded to what? To 2 oxygen. 2 oxygen. This is the skeleton of the molecule. Rule number 3 here states that subtract the bonding electron from the total number of valence electrons. So bonding electron, I have 2. All right, there are 2 here, 2 electrons, and 2 electrons on this side. So if I subtract that, this will be what? This will be minus 4, remain 14, remain 14 electrons remaining. So out of the remaining, we give each oxygen, the external atom, take first priority in. Remember, we are 14. We have 14 electrons to work with. 14 electrons. 14 electrons. So if I have 14 electrons, all right, if I have 14 electrons, oxygen take first priority. All right, in satisfying the octet rule. All right, oxygen take the first priority. I didn't mean that. You don't see that. Let me just erase this. All right, let's see. I meant to put the 2 electron there and this one right there. And our views so far are 12. So 12 remain 2. 12 remain 2. 6 here on either side. The 2 charge goes and it got to be paired them up. You don't distribute single. Don't put one at the top, one at the bottom. Electrons are paired up. If you do the inspection for the octet rule, rule number 4 here, make sure that the all atoms satisfy the octet rule. If it does not, chances are you need to make a double bond or triple bond. Need be. If you look at the molecule right now, sulfur has 6 electrons. Sulfur has 6 electrons right here. 1, 2, 3. Yet we need 8. Each of the oxygen here has 8 electrons. It satisfies the octet rule. So in this case, we will use the 2 electrons on one of the oxygens to make a double bond. So I'm just gonna erase here. and mega double bond on this side, and that is the Lewis structure for sulfur dioxide. Sulfur dioxide. I've ended up with a double bond, so I had to do the inspection. The only way you'll end up with this double bond or triple bond is when you try to satisfy the octet rule on all the atoms in the molecule, and you don't have any other electrons to satisfy the octet rule. You remove what is on the external atom to mega double bond or triple bond, mega double bond or triple bond. That's what I'll do in terms of double bond. Don't try to create electrons. Don't fall in a trap and say, all right, maybe if I do this, let me just take back this and then put electrons here. I've seen students just saying, maybe I need to put electrons here. If you count the total number of valence electrons right here, if you count the total number of valence electrons I do have here, it is 20. Yet rule number 1 states that we should have 18, not 20. Matter cannot be created or destroyed. Don't create electrons from nowhere. Don't create electrons from nowhere. We need a double bond on this side. We need a double bond on that side. So that is how you will create a double bond for part 1. I think in part 1 there are some, all right, there are some compounds with a double bond. You need to follow that guideline, the one I just gave you, in order to complete the Lewis structure for part 1. Any question? Any question on part 1, please? Any question on part 1? Part 2? If you look at part 3, that is what I was, let's see, in part 1, there's some molecules you will see. Look, for example, sulfide ion. I don't know how to draw the Lewis structure for that. You may want to Google out that. I think you did a pre-lab. So that's what you will do for part 3. I said, guys, if you're gonna look at that. Any question? If there is no question, I want to thank each and every one of you for tuning in today. Please, next week, during our final tune in the same time, I'll be here. A couple of you asked questions regarding whether, you can do at your own free time. I don't want to do that. Suppose it is in the 11:59 p.m. and you're trying to do the final and then the system kick you out and then I'm asleep, or, or you're doing 11 a.m. in the morning, I'm in another class, and, you send me an email, it takes 3 days. It's better like, you take the exam. If you, something happen, I'll just be there and then we get it done in one sitting without going back and forth. Just in case, something happened, I should be there to respond to your question. Other than that, thank you. I really appreciate for putting up with all this disruption. The lockdown has really disrupted not only learning, even our daily life. The weather is so nice out there. You can't even do anything with your friends. So nevertheless, next week I'll see you. Be on the lookout. I'll send more information through. I'll send out information through Canvas. I'll post today's lecture on Canvas and send you as attachment as a link on YouTube. Thank you, everyone. See you next week. Professor. Yes, you have a question.
There's a question in the chat. Somebody asked.
Oh, there's a question. Let me see. All right, it was hidden somewhere. Yeah. So the exam will be. Yeah, it will be open 1 o'clock. Yes, I'll be here. I'll be here. Yes, exactly 1 o'clock. What has to be? It is on the same day, Thursday. Same time, same day, Thursday, 1 p.m. I'm assuming that, you are taking other classes, you have other errands to run. And when you sign up for this course at the beginning of the semester, you knew that this is the particular time. And that's why I don't want to hold lectures like 9 a.m. in the morning. You know, we didn't plan that way at the beginning of the semester. So it's gonna be 1 p.m. on Thursday. Any other question? Thank you, Sabrina. Thank you, Stephanie. Thank you, Eric. See you. Have a great weekend. Be safe. All right. Social distancing. Wash your hands, and we will be safe. We will make it. All right. The class is ending now. Thank you.